Okay, so did you realize anything? Because it's now recorded. Side of the participants.
Yeah, there's a
You
like a automated voice announcement, and also
okay, but no, you were not asked. You were not asked.
we were told, basically we were asked if we want to continue even though the meeting is being recorded, and otherwise.
So this happened. Okay.
Yeah.
Okay, we are still 13. Okay, so let me share the screen. Let's okay. Okay. Fine. Good. Okay. Right. Okay, I'd say then let's start the lecture. So we are now in these chapters on Grabner basis. So last time we introduced the concept of a term order, and we will now continue with that. So the point is we want to discuss some concepts and algorithms that really allows us to manipulate polynomial ideals and solve computational problems. So last time, okay, we were looking at monomial ideals. So what is a monomial ideal? Okay, so it's an ideal in the polynomial ring in n variables over a field. And it's called monomial when it's generated by monomials. And we figured out last time monomial ideal is generated by the monomials contained in I. Okay.
The board is blank as of now. I think maybe not the correct board isn't showing.
I see that you cannot. Let me try again. There's a problem. Oh my gosh. It may have to do with the recording, huh? Now?
I think it was last time the same problem, and it works now. Yeah.
Now you can see it.
Yes. Yes.
Maybe maybe I made an error. Okay. So the definition was a monomial ideal is an ideal generated by monomials, but then it's easy to show that it's generated by the monomials contained in I. So we can describe monomials in a combinatorial way. So let's look at the set of monomials contained in it. So monomials or terms, actually I call it terms, are encoded by their exponent vector. So I assign to this monomial ideal the set J of exponent vectors alpha such that the term x to the alpha is in I. Okay, and this satisfies this property. Okay, whenever I have alpha in J and I take any beta in n to the n, then I form the sum alpha plus beta, and I get an element in J. So this set J is closed under addition with any element in n to the n. And why is that? Clearly, if you translate it, what this means, maybe I can write it here. Okay. So this just means take x to the alpha in the ideal, multiply with any term, you stay in I. So this is okay, because ideals are closed under multiplication with any elements. I have this property. Okay, and now I call. Okay, so a set J, subsets of n to the n, with this property I call an ideal of the monoid. Okay, call subset J of n to the n is property an ideal? N to the n. Some people say it's an order ideal, but it's okay, right? So it's a combinatorial condition. So we have a bijection. Okay, so we have the monomial ideals. Okay, in the polynomial ring. And on the other hand, we have the ideals in n to the n. Okay. So this is the map I goes to j. It's a bijection. So you see the field doesn't play any role. The coefficients are irrelevant. It's only about the terms containing the monomial ideal. Good. So then we say, or I can say a subset B of J generates ideal J if, okay, so now I write concretely what this means. So for all gamma in J, there is an alpha in B, okay, and there is a beta in n to the n. Looks a bit complicated, but it's not that hard, such that gamma is alpha plus beta. So this condition here, I can also write this way: alpha is less than or equal gamma component wise, or I can write it this way. Okay. So what does this mean? If you translate back, it makes a lot of sense. I mean, for all, right, any x to the gamma, you can write in this form. Okay, x to the alpha is in my ideal, x to the beta is a term. So it's actually, it's in one-to-one correspondence with the definition of the set of polynomial generates an ideal, only that here we only talk about terms. So exactly that. So here is this is easy to visualize. Let's have a picture. Okay, so here I have a drawing of N2. Okay, and then have a couple of, let's say I have these elements. Okay, they encode monomials. So now, what is the set generated by these 3 points? I mean, what is the ideal generated by these 3 points? So what do? Let's say you take this point, and then you assign to it all the points that are component-wise larger. Okay, then you get this. For this point, and here. So this order ideal is now can be drawn, okay, as this shape. So all the lattice points in this staircase area, okay, form this order ideal J. Okay, it's very combinatorial. Any questions on that, or? Okay. So let's prove a result about these ideals in n to the n. There's the following theorem. Okay, let me change color. So this theorem is sometimes called Dixon's lemma. Dixon's lemma. Okay, it says, first statement is, any ideal J in n to the n is finitely generated. We'll prove that in a second. The second statement is, okay, if you have a set that generates an ideal, okay, this set can be infinite, but there is always a finite subset of it generating the ideal. Okay, any generating set of J contains finite subset, finite set of generators. Okay, so this is quite important, this Dixon's lemma. So you may have heard already about the Hilbert basis theorem, which says that any ideal in a polynomial ring, infinitely many variables over a field, is finally generated, or it says the polynomial rings are Noetherian. This will be a consequence of this Dixon's lemma. So it's an important result, actually. Okay, over this, let's, okay, Beweis proof. I don't know, I switched language. This is all on the recording. Proof. So let's show one by induction on N. Okay. So the induction start. Of course, J shouldn't be empty, otherwise there's nothing to show. Let's do the induction start, N equals 1. So I have here, J is a non-empty subset of N to the N, possibly infinite. How do I find a generator? Question to the audience. I have a subset of N to the N. Okay, N is 1, sorry. Of N. So subset of N. No, sorry.
Just pick the smallest element.
The smallest, exactly. I just take the smallest. So I take, let's say alpha is the minimum. Okay, and then alpha generates J. Okay, so that's very easy. Induction step. N is now greater than 1. So, okay, let's look at the projection pi from N to the N to N to the N minus 1. So I will forget the last coordinate. So let's say x1 up to xn is mapped to x1, xn minus 1. Forget the last coordinate. Okay, then I map my ideal J. Okay, I get an ideal in N to the N minus 1, and by induction hypothesis is finally degenerated. So this is an ideal here. Okay. So the induction hypothesis tells me there is a finite subset. Let's call B. Okay, how do I write it? This way. This finite system B generating this. Okay. Good. So what else to do? Okay. So of course we need to need more. The B is not enough. Okay, and the B is also in the wrong thing. Say, so if I have an alpha in B, then it comes with a nth component. Let's call it M alpha. Let's say alpha M alpha is in J for alpha in B. Okay. This is always because B is a projection. Then let's say M is the maximum of all the M alpha. not the maximum. Yeah, okay, the maximum. So, okay, but this is finite, so this is well defined. Right. So what we do now, let's look at slices of our ideal J. So for I in N, I will slice at level I in the last coordinate. So define Ji consists of those alpha in N to the M minus 1 such that alpha I is in J. So I hope you, okay, if I don't know if okay, this is my picture of J. So and if I'm at level I, okay, then I would cut here. Okay, and so what I get here, like this, would stand for that. Okay, so I slice them at different levels. Okay, and this is an ideal. Here, which is very easy to check. Okay, and then I can apply the induction hypothesis to all these ideals. Okay, induction hypothesis tells me have finite generating system EI for JI. So for each slice, I have a finite system of generators. Now what I will take the union of all these generators. Take, right. Of course, I have to do it right because this is at level I. So I will add here in the nth component the I. And then I take all those up to the level m minus 1. Okay, I have this. And then I combine this with E times M. And the claim is that this finite set will generate my ideal J. Claim this generates J. Okay, so let's check. Okay, let's see. Let's prove this claim. Maybe here. Okay, let's assume I have an element gamma I in J. So there are two cases. So case one, if I is greater than or equal M, okay, then what I will do, gamma is of course in pi of J. So I can write it in the following way. So there is alpha in B and there is beta in N to the M minus 1 such that gamma is alpha plus beta. And then I can write gamma comma I is alpha comma M plus beta I minus M. Okay, now I see. Right. Now look at this element. This is here, okay? Alpha comma M. Alpha is in B and I'm at the mth level. Okay. On the other hand, case 2, I is less than M. So then I know by definition the gamma is in this I slice, okay? So there is an alpha, a generator in BI, and there is something. Let's also call it beta, local variable, beta in N to the M minus 1, such that, again, gamma is alpha plus beta. And then I can write my element this way, alpha comma I plus beta comma 0. Now I see, maybe we can do it in green. Alpha comma I is here. Okay, so I've shown the claim. Okay, and I'm okay. Part 1 of the statement is proven. Okay, I've exhibited a finite system of generators. Okay, and okay, finally, this shows part 1. Part 2, let's also show it. That's pretty easy. Looks maybe a little bit pedantic, but let's do it. So what do we need to show? It says any generating set of J contains a finite set of generators. So let's assume B is a generating system. Let B generate J. Okay. And I proved in part 1 there is a finite system of generators. So let E be finite. And generating. Okay. So, okay, but they are not related by inclusion. But now I say the following. Okay, for all, take any element gamma in B. Okay, because E generates, there must be an alpha, say, depending on gamma in E, such that, okay, how do I write it? It would be best to write this component-wise. So I'm a little bit, I should have introduced that. Okay, here, maybe let's do it in orange, component-wise. So let's use this notation, alpha less than equal gamma with this index C component-wise. Should not be confused with term order. So it means pictorially, if you have here an alpha, the gamma is in this quadrant, generate, okay, with the down left corner alpha. Okay, so with this notation, sorry for that interruption. So I can write it this way. For all gamma in B, there is an alpha in E with this relation, okay? So now let's just take this set, the set of the alpha index gamma, where gamma is in B. So this is a finite system of generators for J, because the set is finite, because B is finite, and it generates because that's all we need. I mean, we only need this. Okay. Okay, and this is the proof.
Sorry.
Yes, question?
So let B generate J and then let E be finite.
And generating J. You cannot read it or? So exists by part 1.
Yeah, okay. Yeah.
So, okay.
Yeah.
So this is a little subtle, but yeah.
Can you show, please, the definition of this C again, of this C relation again?
Okay.
Just for a moment.
Sorry, I mean, you cannot scroll up. That was
Just
a bit unfortunate. This is just component-wise.
Okay.
Should not confirm with term order. This is component-wise order. It's not a total order, okay?
Okay.
Okay. So, yeah. Actually, this Dixon's lemma is not that harmless, actually. So I proved it. The proof is not a long proof. But if you want to have quantitative statements about the size, okay, of generating systems, this can be complicated, okay? So it's not that simple as it may look. if you, but we will not address quantitative questions in this lecture. Okay. So what do we do now? So there are important consequences by Dixon's lemma. So let me put some remark for you as an exercise. You can easily figure out. Right. So as you probably can see already in the picture, if you go back to this, let's go to this picture, the white one. The question is, we have a finite system of generators, and then we may wonder about minimal system of generators. Minimal, okay? In the sense that you cannot remove any element, otherwise it will not be generating anymore. And the statements that I want to make is that minimal systems of generators are unique. And I mean, you can see it in this picture. I mean, in this, it's always, you have this in the 2D case, you have these corners, okay? Finally, many corners. These form the minimal system of generators pictorially. I think one can see that, okay? But of course, in general, it's a high dimensional situation, and then maybe it's not so obvious anymore. So, okay, the remark is this. Let E be a minimal system of generators of J, in the sense that you cannot, okay, if you take away any element of B, it will not be generating anymore. Also minimal with respect to inclusion. Okay, then B is contained in any generating system. Then B is contained in any generating system of J. Okay. Okay, and if this is true, then it follows there is a unique minimal generating system. Hence, J has a unique minimal generating system. Okay, so this is a unique minimal generating system. Okay, so I leave it to you as an exercise. It's an easy exercise. Basically, what you think, you figure it out yourself. Basically, the argument here for part 2, you just redo it and then you see it. Okay. So, but this is a nice situation. I mean, often in algebra, usually, I mean, you look at system of generators in all contexts, and usually it is not minimal. Let's say you have vector spaces, finite dimensional vector spaces. Minimal systems of generators are bases, okay, but they are not unique, no, or in groups, or they're not unique. Here it is unique. It's in a way, nice situation. Okay. Okay, right. So now corollary. Okay, the corollary, maybe I put it here. Corollary has 2 parts. The first says, it is now obvious, it says every monomial ideal is finitely generated. Every monomial ideal in a polynomial ring over some field is finitely generated. Okay, and has a unique, okay, a unique minimal system of generators consisting of terms. I mean, it is just a rephrasing of what we have shown, because these ideals in n to the n, the monomial ideals, they are in bijective correspondence. So this we know already. 2, this is interesting. So let's say I have a term order, okay? Okay, you remember what was a term order? Maybe I should recall what was a term order. So I had this notion of terms, okay, products of variables, so where the coefficient is 1. So the terms are in bijective correspondence with the exponent vectors. So in a way, n to the n is the set of terms in this encoding. And then a term order is a total order of the set of terms with 2 properties. So the one term, maybe I recall it, 1 should be less than any term. Or in other words, I mean, if you write it in terms of exponent vectors, it would mean that, okay? So this is the... On the other hand, this term order should be compatible with the monoid operation. So the other operation, okay, was this, let's say x to the alpha less than x to the beta, then x to the alpha times x to the gamma less than this for all gamma. Okay, so maybe move this somehow elsewhere. So this was term order. Okay. Now, what do I want to say about term orders? The statement is any term order is a well ordering, and this means any non-empty set has a minimal element. So any term order okay, I write it on the polynomial ring, but actually it's just about the exponent vectors. Any term order is a well ordering. This means any non-empty set of terms has a minimal element. Okay. Okay, this is the well ordering. Actually, this is maybe okay. Maybe you can, let's put a remark so you understand. So remark. Okay, the usual order on n is well ordered. Okay, we know any non-empty set has a minimal element. Actually, this is one of the defining properties of natural numbers. But the same, that natural order on the integers is not a well ordering. Because, I mean, there are arbitrarily small elements. You see that? Okay. Right. So this any term order has this property. I can also rephrase this as follows. Instead of say equivalently, instead of this characterization, I can also express it this way, that there is no infinite strictly descending sequence. So maybe right here, equivalent. There is no sequence, okay, infinite sequence, strictly descending, let's say here, 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 etc. And this strict is just a strict order order coming from the term order. Okay, so it means, so this, for instance, this means, okay, this is less than this in the term order, and they are different. Okay. Okay.
Sorry, I
Yes.
don't. How does the well ordering property? How does that follow from?
It's not proven yet. It's a corollary, and I have to still prove it.
Okay.
If that's your question, I just wanted to. I realized that the notion should be illustrated. Okay, I illustrated it, but now let's prove it. Right. So I think part one, I think that's clear. Okay, by Dixon. This is essentially Dixon's lemma and remark. The remark was about the uniqueness of the minimal system of generators. So, but two is not clear. So let's do it. We can do it indirectly. Assume we have an infinite strictly descending chain. So have infinite. We have x to the alpha 1 strictly larger than x to the alpha 2, strictly larger x to the alpha 3, etc. And it's an infinite sequence. Now what we do, the trick is we look at the ideal generated by the monomials. So look at ideal generated, let's call it I, generated by all this. Okay, I have infinitely many generators, but I know by Dixon's lemma, this ideal I is finitely generated. Okay, it's finitely generated. So therefore, as by Dixon, I conclude there is some n such that I is generated by the first n of those. Okay, after taking finally many, I can stop. And then I see, okay, then if I look at x to the alpha n plus 1, that's in the ideal I, okay? But the ideal I is generated by this n many. So there must be some index I less than n. Okay, now I need space. Such that x to the alpha I divides x to the alpha n plus 1. Okay, the x alpha n plus 1 must be a multiple of one of the x alpha I. Okay, and this again, okay, this means alpha I less than equal alpha n plus 1 component wise. But then as we noted, if we have the divisibility relation, then we also have this relation with regard to any term order. Okay, if one monomial divides another, then it always implies this order relation with respect to term order. And this is a contradiction because I assume the chain to be strictly descending. Okay. Right. Okay. So the Gröbner basis is all about the term order. So let's assume we have a term order. So we have ordered the terms, but we also want to order monomials, not just terms. Okay. Polynomials are linear combinations of terms. So how can we extend this? This is the next topic. Okay, let less equal be a term order on the polynomial ring. Okay, we extend okay, from terms to polynomials. So I want to compare any two polynomials. And I define this recursively, okay? Defined recursively. Recursively. By, okay. Okay, we had this notion T of F. I hope you remember T of F was the set of terms, okay? And I do it recursively or inductively by the cardinality of the term set of F. This is the set of terms. Okay, so what I say first, 0 is less than or equal G for all G, for all polynomials G. Okay, I just write, okay, this is my notation for the polynomial ring if there are many variables, okay? And 2, let's see whether I can, if F is non-zero, a non-zero polynomial, then I say F less than or equal G. So F and G, okay, I should write maybe G. So what does this mean? Okay, so either we had these notions of leading term and leading, okay, coefficient. I hope you remember that. So the LT of F, okay, is the leading term. So I have a polynomial which is not zero. It has a set of terms, and then the leading term is the largest one. Okay, this is the leading term. So I compare the leading terms. So now if the leading term of F is less than the leading term of G in our abstract term order, fine. But if they are equal, same leading terms, then now okay, what I write now is now defined recursively. What I do is this. I remove from F the leading monomial. So the leading monomial includes the coefficients. The same on the right-hand side. I remove the leading monomial of G. And then I compare, okay? And this here, okay? Okay, this is already defined by induction. Okay. Note, so this makes sense because when I remove from F the leading monomial, I get at least, I get one term less, okay? So this is in cardinality strictly less than the set of terms of F. So this procedure makes sense, it's defined. So I feel I should, okay, I should recall these notations. So what I had leading monomial of F is leading coefficient times leading term. Okay, always leading term, leading coefficient. The leading coefficient is in the field, and this is the leading monomial. Maybe a little bit pedantic, but it's important, this context. Let's do an example, okay? Example. Okay, the simplest case is n equals 1. When n is 1, there is only one term order. Okay, you just compare by the degrees. So let's see. Okay, what do I have? 2x to the 6 plus 5x to the 3 plus 1. And I compare with, let's say, x to the 6 plus x to the 3 plus x. Now the question, I have these two polynomials, and the question is, which is larger than the other? Okay. So what do? I compare, let's see, By definition, here is the leading term of this guy, the leading term, or the leading monomial of the f and the leading term of g. I have to compare these leading monomials. The coefficient is irrelevant, okay? So only look at the terms. So what I see, that they have the same term. So here I have x to the 6, and here I have x to the 6. They are equal. Okay, so I will remove the leading monomial. So I remove these things and compare now these two things. Okay. So that's again, okay, let me again, maybe in another color, indicate the leading terms. So here is the leading term of this and this. Again, they are equal. So I remove this, and then I'm left with this one, which is, okay, x to the 0, and this. Now I see, okay, 1 is less than x. Okay, therefore, I have this. So this is important that you understand this for all what follows. If you compare two polynomials, you think of, okay, you write one and the other, and then you compare them term-wise. Okay, you start with the largest, okay, and you compare. It's kind of, here it's kind of a lexicographic thing, okay. You look at those positions in the one variable case where for the first time terms differ. And then what you see there, that counts. Okay, like in the lexicographic ordering. Right. So
To be sure, a short question.
yes.
So there we really don't mean the minus, we mean take the leading monomial away there, where there is
But
the
minus is taking away.
Okay.
It's a subtraction. But the effect is I have
oh
removed
yeah,
it.
right. Or I
Minus is removing.
yeah,
With the
I
right coefficient though, okay? That's why I have not
Okay.
leading term,
right, right.
but so
Not
okay.
leading term, but
Not leading
minus
term,
leading
but with
monomial,
the
right.
yes.
Okay.
Okay.
Sorry.
Yes.
What would happen if, say, the last monomial on the left-hand polynomial will say 2x?
Nothing. Because the coefficient is irrelevant for this comparison.
So then would we?
Same. Let me, okay, I can.
But then it wouldn't be small. No, I mean on the left hand. So if we had,
on the left-hand side.
yeah.
Okay, on the left-hand side, what should I put on the left?
So instead of 1, we would have 2x.
Okay, 2x. Okay, good. So, right. So then we would end up with very good question. What do we get?
Well, I want to say that then the left would be larger, but also
Right? Are you sure? No.
I'm not sure because we
No.
also said that
But if I replace this by 2x, I would see that the left hand is less than or equal to the right hand, but not strict. Okay. Actually, I was about to make a remark which explains this. Okay. A very good question. So, okay, what I wanted to say is this, what I just defined is reflexive. So f less than or equal f, it's transitive. You know what this means? It's total. But, so total means I can compare any two, but it's not antisymmetric, but not antisymmetric. And this is what you just, you were puzzled about that. When f is less than or equal g, and g is less than or equal f, you do not, that doesn't imply that the polynomials are equal. This just means that they have the same set of terms. If and only if. So in the example that you proposed, where I replace 1 by 2x, I have two polynomials with the same set of terms. Okay. So, okay, so this is easy to check. Good. Maybe just to be clear, write f strictly less than z if f less than or equal and different. Okay. So okay. Now I have another proposition. And what does it say? Before we had this well-ordering property. So if I move up, where was it? Here. Okay, it was this. Term orders are bell orders. There are no infinite strictly descending chains of terms. Okay. And now, as it turns out, we have extended the term order to polynomials, but we still have this bell ordering. That's what we want to prove now. Okay. Proposition.
Did you want to say that the term set of f should be not equal to term set of g? When you write f is strictly less than g?
I think I want to, that's a good comment.
Because I think otherwise we would have this strictly declining sequence, no?
How?
Because
Oh, that's right. I mean, I think you are right. Thank you. Let me correct it in my notes. There was, yeah, that's right. Oh, okay. No, in my notes it was good. I could also, I think, okay, my notes were good, but I cannot even copy my notes. I think I wanted to write this. But this is equivalent to what you said. Okay, otherwise good. Proposition. There is no infinite sequence. So F1 strictly larger than F2 strict F3, blah, 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 of polynomials. So it's again Bell ordering property.
So just a short question
Mhm.
about well ordering.
Yes.
So if I understand correctly, there's no unique least or minimal element in each chain, because we have the case that there may be multiple polynomials that may be minimal in a chain.
In a chain. But if the chain, a chain is totally ordered, so I mean, in such a chain, either there is no minimal element, or it is, okay, I don't understand. Are we talking about finite or the infinite chain? So I'm confused.
We just had the case that two polynomials we just discussed that the ordering is not antisymmetric.
Yes.
So so in order for the polynomials to be both larger and smaller than each other, they need not be the same. Because we don't have antisymmetry. And now I'm asking myself, does this mean that if we have a chain that contains both f and g with this property, and assuming f is minimal in that chain, is g also minimal?
Okay, I'm not sure. Um, hmm. I'm not sure I really understood this question. I mean,
So, I mean, take F and G such that F is less than or equal G, and G is less than or equal F. Then we know. Then we know they have the same term set. And
but minimality, are we talking about the fixed polynomial or about the set of polynomials or an ideal of polynomials? I'm confused.
a set of polynomials.
A set of polynomials. Ah, okay, I have a set of polynomials and then
and you have two polynomials with this property.
Ah, right, of course. Ah, okay, now I think I understand. But of course, minimal elements, I mean, they will not be unique because we disregard the role of coefficients. I mean, say you have, is it that what you want to say? I mean, say if I have a term, which is minimal, but you multiply the term by 2, will also be minimal. So, but this is,
Okay.
That's for sure. Okay, sorry, took me some time to understand. Okay, but this proposition, so this will be relevant because later on when we investigate Gröbner bases and so, or even we will look at an algorithm and we have to show that the algorithm terminates, and this will be due to this proposition. So how can we prove it? Let's do it. Let's do it indirectly. So I assume I have such a sequence, okay, strictly descending of Fi. So I give name to the terms that occur in Fi. So let's say the largest is alpha I1. This is strictly larger than X alpha I2 and so on. And it goes up to alpha IMI. Let this be the terms of Fi. So what in for each Fi, I look at the term sets and I order them. Okay. Okay, and then I think of them in terms of a table. So actually it would be nicer actually just to write the exponents, but let me write it this way anyway. So I look at this table. Okay. So I have X alpha 1, 1, larger X alpha 1, 2. Okay, it's a bit maybe a waste to write all the X's all the time, but let me do it. Now, what can I say about this? Okay, now I compare here. Okay, and I know this is greater or equal. That's how we define, because here, this row corresponds to the terms of F1, this corresponds to the terms of F2, because F1 is larger than F2, so I must have this relation, okay? And then I go on. Etc. Okay. So now let's just look at the first column. So maybe look here, what's happening here? Let's look at the first column. Okay. I look at the exponents that appear in the first column. Sorry, that was something that I didn't want to do. Okay. And I apply Dixon's lemma. So look at first column. So the Dixon's lemma tells me this chain, I have this infinite chain. it must stabilize. Now the Dixon implies there is some index I1 such that for all I greater than equal I1, I have this X alpha I1. Okay, this is a bit I11, sorry, equals X alpha I1. So in a way, you look, maybe I shouldn't write the x's. You just look at the exponents, okay, going down, and then at some moment it stabilizes. So maybe I can have a drawing here. I look at this. Okay, I do the table again. So this is my table. Okay, I look at the first column. Okay, and here, okay, here is the index is I1. And from this index on, I have all the same number here. Okay, I have a number, maybe an orange number, but they are all equal. Okay. Okay, stabilizes. Okay.
On the is it X alpha I11 equals X alpha I1?
Alpha. Can you say it again?
Just the last equality on the.
Yes.
So
Oh, yeah. Sorry. That's what I wanted to. So this actually means it's just a stupid way of writing this. Okay. So here in this picture here, you see, they are all equal. Okay. Now, right. Let's see what happens if we now remove. Okay. Next step. Maybe define. Okay, fi twiddle. What is that? I remove from fi the leading monomial. Okay, I can do that. And then note that, okay, what do I say? fi1 twiddle is larger than fi1 plus 1 twiddle, etc. Right. So in a way, I mean, what I want to do, I want to, okay, I want now to omit the information in the first I-1 row, okay? Goes not interesting anymore. So I cut my table. I only look at the lower part. Now why is this true? What I wrote. Yeah, because I know, okay, I know this fi1 is strictly larger than fi1 plus 1, okay? But these polynomials, they have the same leading terms. Okay, same leading terms. So by definition of the order on the polynomials, I must have this. Okay. Okay. Now I have this. Now that the point is, of course, we will now, okay. Now we have again, and okay, we have removed, okay, I should write, okay, remove first I-1 rows and remove first column in my diagram. Okay. Okay. Then I have I have this sequence here. Again, a sequence of polynomials strictly descending. But what I note is, okay, let me state it and then claim all remaining terms are strictly smaller than the X alpha I11. So why? Color, what is a good color? Pink. So this is here, okay? This is the alpha I11, okay? Right, let's say you are here. Here, okay? There's a term here. Then this term, I mean, is strictly smaller than what you have here, because this pink thing is not in the first column. I've removed the first column, okay? And this is equal to that, okay? Right. So, and then I can just proceed recursively, and I obtain an infinite strictly descending sequence of monomials, and that's a contradiction. So proceed recursively, obtaining strictly descending chain, strictly descending infinite chain of terms, I should say infinite thing. This is a contradiction to the Dixon, okay? Okay, so, right. So I used Dixon's lemma twice, okay? I used it to say where to stop when watching at the first column, and here again. Okay. So maybe you need to think a little bit about this proof. It's not completely simple, the argument. Okay. Also, it's not very constructive. The proof is not constructive. I mean, doesn't tell you where it happens. Okay. So we will use this proposition to show that certain algorithm will terminate, but the proposition doesn't give useful information when it actually terminates. It just says it terminates. Okay. It's not constructive, but on the other hand, it's relatively easy to show. Okay. Right. So, okay, there's still some time left. Let me explain now. Let me move to the next section. This will be 2.2. It's about the reduction and the division algorithm. And a division algorithm. Okay. So when we deal with polynomials in one variables over a field, then we have this wonderful division. Okay, we can divide one polynomial by another, division with remainder. Everybody knows division with remainder. You can do it for integers, but you can do it for polynomials. And I know in German gymnasiums and schools, you have to do this. You learn how to do this. Okay. So, but what happens if I have polynomials with more than one variable? Can I still do that? Okay. And the answer is yes, you can do it. It makes sense after you have chosen the term order. So, okay, the answer will be for every fixed term order, there will be a division algorithm. Okay, good. But because it depends on the term order, it's maybe not so nice than just for one variable, but it still will be useful. Okay. Right, so what I do, okay, I have a set, a finite set of polynomials. I denote this with capital F. It consists of F1 up to Fr. So these are polynomials. And I assume the Fi's in my set are all non-zero. Okay, fix a term order. Okay. Okay, and then it's the following notation is also nice to have. Okay, let's define leading. Okay, how do I write it? LT of F. What's that? It's the set of leading terms of the polynomials that I have at hand. Okay, so each fi has a leading term because it's non-zero. The set of those leading terms I denote with LT capital F. Okay, so what do I want to do? It's very simple. Maybe let me first illustrate it with a picture before I write it formally. So illustration. Okay, just pictorial. So here is my polynomial f. Okay, I have ordered the terms, so I can write the terms in a certain order. So I mean, there is something, 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 something. Maybe here is the term lambda t. Okay, the monomial lambda t, and then it goes on. So lambda is in the field, and t is the term. Okay. Okay, and down there, I write some fi, and this starts with the, here I write the largest one, so I have leading coefficient fi times leading term fi plus blah blah, all other monomials or terms are smaller. Okay. So now hopefully I assume, okay, I assume the leading term of fi divides t. Okay, so maybe the picture here is my leading term of fi. Now, as it happens, this divides this t. Okay, let's assume this is the case. Then what can I do? I want to subtract from f a multiple of fi in order to kill this monomial. Okay, I want to remove this. Okay, and how do I do that? It's okay, you know that, of course. It's like in the division algorithm, or it's also the same with Euclidean, with Gaussian elimination. So what do? I will multiply fi with t divided leading term of fi. Okay, if I write down what this is, okay, I get the right term, but not the right coefficient. So I will also multiply with lambda divided by leading coefficient of fi. Okay, and then if I write down what it is, this will start with lambda t plus the remaining terms. Okay, so this is multiplied by certain terms, so I will get t. This is multiplied by a number, I will get lambda. So you see now this and this are identical. And if I subtract, lambda t cancels. Okay. When subtracting, this from f, lambda t cancels. Okay, you know this trick. Okay, it's like division that you know for programs in one variable. When you do Gaussian elimination, we also do this trick. Okay, we do this here. Okay, so that's what we do. And then what we say, right. So after doing this subtraction, we get another polynomial, and we call this a reduction from f in one step. So let me now write the formal definition. Okay, let f be a polynomial in many variables, but I just write it this way. It should be non-zero. G is another polynomial. And then I say f reduces to G mod f modulo capital F in one step. Okay, I know it's a bit awkward, reduces to G in one step, okay. Okay, but we will have a symbol for that. If, okay, there is a term of F and there is fi in f such that leading term of fi divides t, and this g is defined as f minus, now I just, copy this. Okay, this, yeah, this is the case where lambda is the coefficient of t in f. So this is exactly what I explained in my illustration. We write also in symbols. It's good to have a symbol expressing this. We write it this way: f goes to g, okay, modulo f in one step. Okay, so this is one reduction step. Okay, so should we have any? It's always good to have examples. Okay, example. So let's use the lexicographic ordering. And x is larger than y, and let's just have one example. Okay, f is like, okay, I can take anything, x. Okay, so this is f, and then I only have f1. Okay, just one polynomial to divide. Let's say it has 2x, y, z plus y. Okay, now I want to reduce f mod f1. Okay, so let's see. So I have to look what at the leading term of f1 is x, y, z. Okay, and then I look at the terms of f. Which term of f are divisible by x, y, z? Actually, the only one is this. Okay, so right. So I will focus on that, and then I have to multiply with what? With y, I think, y squared. So f1 times y squared. If I do this, I get, okay, here I get the right term. Okay, but here it has a 2, so that's why I would put 1/2 here, so I get the right coefficient. Okay, and then I continue. This is y 1/2 y cubed. Okay, and now I subtract. Maybe I write it g, I subtract. What I get is this. This one, I mean, you see, this one cancels, the middle one. Okay, they will cancel. And then what I get is minus 1/2 y cubed plus y. Actually, I think, and okay, I wanted to put this, let me put the square here. I think I wanted to put the square here, not to. So then it's that. Okay, very simple. No deep math. It's just calculation. But okay, it shows what we are doing. So maybe, okay, this remark is important. When I reduce f to g modulo the set f, then always what I obtain, g, will be less than f. So maybe write me this way. Okay, when I make a reduction, I always get a polynomial that is strictly smaller in the sense that we defined it. Let's maybe go back to the illustration to explain this. Let's illustrate this here. Because when we form this G, so what do we do? I mean, look at the here. Okay, I have my f. I think of the set of terms. Okay, I mean, all these terms here that are larger than t, they are not affected, okay, when I form G, okay? Okay, I compute f, I compute this, I compute f minus this to obtain G. So all of these terms here, they are not affected. The first term where anything happens is here, and this is killed, okay? Well, in f it's there, but in G it's not there anymore. That's why if f is strictly larger than G in our ordering, okay, the term in f is there, the term t is in f, but not in G anymore. And all the larger terms, you know, not affected. Okay, I think that's the reason. That's important. Okay, maybe I should even frame it. Easy, but important. Okay, so this is good because then this shows that if we do a reduction many times, at some moment it has to stop because there are no infinite strictly descending sequences. Okay, still a little bit more time left, so let's do a definition. Okay, what is a normal form? So f, a polynomial f is called normal form. Normal form mod modulo the capital F if, okay, if what? F equals 0 or there is no G that is, okay, you cannot reduce it any further. So this is not possible. Okay. This. So the idea is you have your F and your collection of polynomials capital F. You want to reduce F, okay? But at some moment it will not be possible anymore. It's minimal, okay? This you call normal form, okay? Okay, this is normal form, and then look, this is just notation. This is useful for the proofs. We say F reduces to G mod F in M steps. In M steps if, okay, I write it this way, F goes to G as before, but I put here a little M, okay. If there is a sequence F0 up to Fm, F0 equals F, okay, Fm is the G, and in each step, okay, I reduce, okay, Fi reduces to Fi plus 1 modulo F, okay, I have this for. So I obtain G from F by a chain of reductions, okay, actually by M steps, okay. Okay, and then I say F reduces to G mod F. Okay, I write it this way. Now instead of M, I just put a star. If, okay, there is some M. Okay, I just did. Okay, it's just notation. Okay, a sequence of one-step reductions. Okay. Okay, my time is over. So what are we going to do now? In a way, I mean, in a way, this is already, we already have the division algorithm. So I have my collection of polynomials F, F1 up to Fr, and another F. Okay, and then I try to reduce until I can't reduce it anymore. So I ended up with a normal form. but this is not, I mean, the algorithm is not defined yet because it's not completely determined. What do I have to do? If you again look here, I have my f. I want to do this division. Okay, I want to this. But if I have several polynomials, say I have two polynomials, f1 and f2, but there is a choice. I mean, what do I do? It could be, I mean, I could use f1. Okay, I take the leading term of f1 and look which term it divides here, and I try to reduce. Okay, but this may be possible. But I can also look at f2, the leading term of f2, and I can also reduce. So there is I have to define which comes first, f1 or f2. So if you order your f, you say first f1, then f2, then it is defined and it becomes an algorithm. Okay. But I mean, what is not so nice about this algorithm, we'll see the result actually depends on the order. Okay, so this is not so nice. Okay, so if you change this order, you have a different result, and that's kind of a mess. So it doesn't look very useful. But the good news is when the set of polynomials by which you divide will be a Gröbner basis, okay, I will define what this is on first day, then the result of this division is independent of the choice of the ordering. Okay, then you get something really nice. You get a well-defined normal form, etc., and you can work with it. Okay, so I think that's the plan. That's what I want to explain you on Thursday. Are there any questions?
Yes, I have a question about this division. So do I understand right that we kind of extended the notion of division to division a polynomial by a set and not just by another polynomial anymore? So we kind of divide by a set. We take a polynomial and we
divide by a set, yeah. Or
Yeah,
actually,
okay.
right.
Or it could
Or
be
by
one
a sequence. Actually, it's rather by a sequence, because once we specify the order, then it will become an algorithm. Yes.
Okay, by a sequence. And is that so that we actually that this sequence does not necessarily have to do? I mean, it's kind of strange. I wonder whether it is. I mean, when we had a field and we had polynomials over a field in one variable, then each polynomial was divisible by other polynomial, and it kind of made sense. It was clear why it is a good thing. We could prove some theorems by that and so. But here it is like it looks very arbitrary.
Yeah, that's right. But you have to be a little. That's true, but you have to be a little bit patient. Okay. You will see once we have Gröbner basis, everything will be clear and nice. At the moment, okay. I agree, it looks arbitrary, not too useful. Okay. You have to be patient. Okay, I think I will now stop the recording. If I can.